Um, so our first homework has 6 small problems.
How's the last one small?
6 small. What?
How's the last one small?
What's that?
Because it fits all on one page.
Now, I think mistakes of 4 pages. So, we're gonna put that on canvas this afternoon. A week from today.
When do you think it due? What?
When's it due?
Monday.
Is it Monday?
Inshallah, next week.
Huh?
Inshallah, not this week, please.
What's that?
Not this week?
Have we already gone over everything that we need for the homework?
So after the examples today, you should be able to submit the homework.
Okay.
So, the last lecture, we have this is the voltage. So, we have the shaft of our motor. Oh, I forgot to bring a DC motor today. How in mind? We gotta cancel class. Oh. Do we?
We're visual learners. I don't see it.
Mr. Tensi, there's okay, so the rest of the talk is here. Talk of the motor. And that motor then the displacement is theta m. So we wrote the KVL, and the current here is IA. So it's RIA plus LADI. So let me just call it I. So we use the subscript A to indicate that it's an armature current. Plus VB. And we said that VB is proportional to what? Angular velocity. Thank you. That's good. And we said the torque is proportional to what? To the current. Thank you. All right, so that gives me, so what happened in steady state? So when in steady state, I said the motor is turning at constant speed. dI dt is what? Steady state, the current is constant, right? So di dt is 0. So we have IA t equal to RIA, RI plus VB. So RA TM 1 KT plus K T W. Okay, so I'm after running the speed torque, speed torque. Okay, right, that's what I'm after. So I'm gonna solve for the torque. Yeah, of the motor is negative kb omega kt over IA plus EN KT over I.
Is that an XT or is that KBK?
No, that's a KD.
Oh, KBKT.
Yeah. Okay? Yeah, great.
Yes.
That comes from this equation.
Mhm.
So, as you can see, it's, I'm gonna sketch the torque. The torque Tm here, and angular velocity here. Okay. Now, can you help me sketch this? So when the torque equal to 0, what is omega? What is omega?
500. Oh wait, no, I thought I was looking at our paper.
You say what?
EA,
EA,
yeah, over KB,
KB,
right?
that's omega,
Yeah.
okay? Yeah, I agree. So when torque equals 0, we can cancel KT, right? So, and then we
Wait,
can,
Why can we cancel KT?
huh?
How can we cancel KT when it goes?
Well, this is because KT is common for all the terms.
Oh, so you just pull it, okay.
Yeah, and then RA is also common for all the terms. Get rid of it. So what we have is EA over KB. Oh, if you
Oh,
don't,
I see now, sorry, I just do the mind, I see it.
okay.
A little
So-
slow.
So EA over KB. Right, when the torque equals 0. Now, when omega equal to 0, what happens? The torque
So it's
of the motor will be equal to EA
KT over
with T
RA.
over RA. Okay? So, this is a straight line, isn't it?
Yeah.
Equation of a is like,
Linear.
yeah, A omega plus B. It's a straight line.
Mhm.
So when we sketch it, it's gonna look something like this. Okay, sorry.
Not drawn to scale.
Oh, but it's a line, right? It kind of look like a line. Well, there you have it. Okay, so this is called omega no load. Okay, the torque is 0. So there's no load on us. Right? It's like you hold the motor. You hold it. right? It's turning, then you just hold it.
Freely spinning.
Yeah. So when you hold the shaft, like let's say this motor is turning, and then you hold the shaft. Yes.
What if, with this, me saying no load, like, are we saying it's like an ideal motor with no internal resistance?
No, like if it's not. So let's say the motor is turning, you don't have anything connected to it,
Oh,
and
okay.
then you cannot hold it down.
Yeah, like hold
Yeah.
the thing that's turning.
Yeah, the shaft. Assume it's a small shaft that you can hold by your hand. Okay, so what are this? Oh, I think I drew this in the other way. So T stall, right? Stall torque. Is that how you spell stall? Like when something is not moving?
Yes.
Yeah.
Right.
And it stops. Yeah.
Yeah, right. So, is the torque when you hold the motor down, when you hold the shaft down, right?
Stops it from spinning.
Yeah, so prevent it from spinning, that means omega equal to 0, right? So when you hold it down, it's not turning, right? So the angular velocity is 0. But you have a torque that's developed, right? That's what we call stall torque, or T stall. Now, when you buy a motor, on the data sheet, it tells you what is the nominal torque that you can apply, right? So, you have a nominal torque, right, on the data sheet, right? So, if you want, you could just go online and pull the data sheet of the DC motor. It will tell you the power, which is the nominal torque times the angular velocity, right? So, nominal angular velocity.
Good question.
Yes?
Do you mean stall torque or stored torque? Like you're storing energy?
No, stall. Like,
Stall is
something
come
stall.
to a complete stop.
It's not moving.
Yeah.
Stop.
Like if you stalled your car.
Oh, stall, oh, okay.
Velocity.
Oh,
And this is nominal torque.
Is it called, what is it called again, the torque load liners and?
It's torque speed curve. Now, so when you buy a DC motor, on the data sheet, they're gonna indicate this for you, the nominal, right? So, and the data sheet might even give you this curve, right? So that means what is constant for this curve is IA, right? The voltage that is applied. So when you apply different voltage, do you agree that the plot is gonna move to parallel to this one to a different location?
Mm-hmm.
Do you all agree?
Yeah.
The slope is going to be the same, isn't it?
Yeah.
The slope doesn't change when you change the voltage applied to it. The y-intercept is the only thing that's changing because that depends on the voltage.
Shift the whole thing up and down.
Yeah, right, so the graph is gonna go parallel to this, the slope is going to be the same,
Mhm.
right? So for applications, if you wanted to use this motor to drive something, you have to find the operating point. So in electronics, you call it what? The key point, isn't it?
Quiescent point.
Yeah. So you wanted to find the operating point for this to work the best. Right. So what happens when you hold down the shaft of of the motor,
Magic smoke.
right? So when you hold it down, at some point, the energy is gonna melt the coil. Right? Because there's no other way for the energy to transfer but to heat, right? So at some point, you are going to melt down the motor. So it's okay to operate the motor in this area sometimes, but not all the time. Right? So if you look on the data sheets, this area is called intermittent operating agent.
Is that where you wanna be?
No, you don't want to be there. You can be there just once in a while.
But wouldn't that be the 2500 be like a medium load, like?
No, so this is where you want to be. Right? That is the nominals. That's where you want to be. Right? You don't want to stop. When you stop the motor is turning, but you hold the shaft down. When you hold the shaft down, the energy, right? Because the power is I squared. So it's gonna generate heat. So when it generates heat, it's gonna melt the coil. Does that make sense?
Yes. Yes.
So the middle dot is the optimal place you want your motor to be at, correct?
Mhm, yeah.
Okay.
I mean, this area, see that area?
Yeah.
You don't want to be there all the time for a long time. Because once you're getting too close to the stall torque, you're going to generate more heat. And it's going to melt down the coil that you have in the motor. Yeah?
Sorry, I just got confused on where you were pointing at.
Oh, okay. Alright, so this is the area.
So
Yeah.
it's okay to be below and to the right?
Yeah. It's okay.
So like past the stall line, but to the right?
Mhm.
Why is that?
This is no load, right? It's this thing is just, it's freewheeling, it's just turning. That's no problem. There's no resistance to it. Yes,
In other words, you don't wanna have too heavy of a load to where you burn everything out.
yeah,
Okay.
right?
Yeah.
So if the load is too heavy, it's
Yeah.
gonna hold your motor down. And then that's what, next thing you know, the smoke. Yeah.
So if you increase the speed but maintain the same torque, that's okay?
Increase the speed and.
So you move to the right, but you stay at the same point on the y-axis?
You wouldn't be on the line.
Yeah.
Yeah, but isn't like, kind of like that?
No, so that means you have to apply different voltage, right?
You
That's
always
what
gotta
it
be
is.
somewhere on that
The
line.
graph is moving up and down, parallel to the one that we drew initially.
We're talking about like gooseneck.
Okay? Alright, so, well, I'm saying this because for your design, since for some of your design, well, maybe not related to this class, you're gonna be dealing with DC motor. You have a motor, you have the data sheet. How can you read the data sheet? Right, so when you pull the data sheet, you're gonna see this graph. And they're gonna give you the nominal curve, and even, I think, homework 2 has something like that. Where I'll give you the motor with the data sheet, right? And I'll ask you to design a system with it. Okay? So, now, so given this speed torque curve, right, you can solve a lot of problems, a lot of questions. So let's do the first example. that we have on that sheet, paper, that I hand to you.
So if you increase the torque, you're gonna get more heat as a byproduct of that?
If you increase the torque,
Yeah, so if you decrease the speed to increase your torque, your torque output, you're gonna generate heat.
so the torque is proportional to current. Yeah? So when you increase torque, I mean increasing the current. Yeah? Increasing the current, meaning what? You have gonna have a lot of loss in the resistor out here in that. Okay, so can you try to do this? So some of these equations, as you're gonna see from next week, are going to become very complicated to solve by hand.
Are we gonna use MATLAB?
So I'll show you how you can just use MATLAB for them. Okay? So I'm gonna show you how you can use MATLAB to solve most of these questions. Okay? So because beyond this, beyond 3112 and 4111, are you dealing with a system that are not small systems? Sometimes. And sometimes you have nonlinear systems. And when you linearize nonlinear systems, that means you have to perform Taylor series expansion. That's what we learned in class 254. And that will generate higher order systems, but still linear, and then you have to solve. But to solve it by hand, that's tedious, so we can just do it in MATLAB. Okay? So I'm gonna show you how we can solve most of these questions in MATLAB. Right? In my experience, there are questions, when I was working, they would give it to me. I don't even solve it by hand. Just go straight to MATLAB, program it to MATLAB, there we go. Right, so I wanted to make sure you know how to use the MATLAB control toolbox. You can design communication systems, you can design satellite systems, you can design vehicle systems, you can design even an engine of a motor, right, of an aircraft in MATLAB and simulate it. So it's very powerful, So I think that the license we got, it costs more than $50,000, right? That's what they were using. So, you can do whatever you can think of. If you're clever, you should pull it off. You can do it in MATLAB. Okay. So, but this one is just a second and third order system that you guys can solve by hand. So let's do this by hand, and I'll show you how we can solve the same problem in MATLAB as well. All right. So in homework, you do that to double check your work. Okay. All right. So can we do number one?
With a little guidance, yes.
No, number one, I think we did most of it, isn't it? So,
The first part, yeah, it's similar.
so you have, you see, this is a symbol of a DC motor, right? So when you see that, it's just a symbol. Yeah. So what does this mean?
I guess that's like the magnet that's
Yeah.
spinning.
Yeah, it's a magnet that provides magnetic field, right? That's what's called a fixed field, right? And then you have something rotating in that magnetic field too. And when you have current, that's it. Okay.
And this creates a DC current?
Yeah, it's a DC motor. You drive it with DC current.
Oh, you're driving the magnet, not the other way around.
Okay, so last lecture we learned how to do this. how to write equation of, the transfer function of a motor. Right, so, I think we did, didn't we?
Yeah, we,
You did one for a circuit.
we went to the.
We didn't see how to necessarily combine the two though from
So we get to this, right?
Yeah.
Isn't it?
Mm.
Yes. So, let's look at this and solve this question. So we have our DC motor. And we have the shaft, which is, we call it the J of the motor and the D of the motor. So that's this equation, isn't it? Yeah? Alright, so let's go to, yeah. My computer is kind of slow today, I don't know why. So, we are going to redraw this as so we have JM here and DM. Right, so we learn how to reflect everything from here to this, to the, we learn how, do you recall how to reflect the J and the D and the K from one side to the other? Do you recall what we did? You don't recall?
When you say one side to the other, do you mean
So,
like
like,
the gears?
Turn this into this. Hey, this is the gear right there. Right? How's the gear? 1,000 to 100 ratio. You recall?
You need to where we can just have torque and the
Yeah.
theta?
Yes. Right?
Mm-hmm.
So we said that you just multiply the J by where you're headed, the ratio from where you're headed divided by the input.
Is it a bad idea to try and just directly substitute for zeta 2 and T2?
Yeah, you can do that too. Okay. I don't know if we're on the same page. So to reflect this JL, right? The J of the load to here, what do? We take the output, right? Whatever we reflect into, over into square times JL, and then dm n1 over n2 square. Oh, you want me to go to the math? Yes, let's go to the math. I don't think you you remember. So we have this.
This is not the second one here, right? Because it's an inductor.
What's that?
Oh, this is, but you have an extra inductor. Or is that LA supposed to be the fixed field inductor?
Yeah, no, when we model it, we kind of say that the inductor value is 0, right? Do you recall? Do you recall that?
Well, I don't, but I heard it now.
Oh, what? Michael?
Oh, maybe. I think maybe
No,
you said something like that.
Yeah, so I even said that here, I boxed it right there.
Yeah, okay. I remember writing it down.
Right, so that's how we come up with this equation, right?
Yeah.
Okay. Alright, so we have this. So this is called N1. And then this is a gear ratio. And then we have this. It's D of the load, J of the load, and 2. So the motor, so if this equivalent to the same thing, let me write it here, because you're going to do this in the homework as well. Okay. So to remove this ratio, what do we do?
Multiply.
N1 over N2, right? Because we're going this way, right? So the output, which is N1 squared, N1 over N2 squared, JL. That's the J of the motor. And then N1 over N2 squared dm. dl.
Where's the DL comes from?
It's the dampener to the right.
Oh, damper, my bad.
So, if the motor has a moment of inertia, that's J. So, and then A and dA, that's what the problem is saying, right? Right, if the motor has this, and then we're gonna reflect what we have from the load to the motor. So the total will be what?
So basically,
JM,
when we write
JA?
the system of equations, we're just supposed to substitute JL for N1 over N2 squared JL.
1 second. And then dm. N2. Okay, what's your question?
So to make the replacement, we're just substituting like the load with, so whenever we have to write JL, we just substitute that with N1 over N2 squared.
Yeah, so when you remove the gear, right? Maybe, should we do an example of a transformer in an electrical system for you to see?
And we can continue with this.
Wait,
No.
When you remove like the N1 and N2 and you combine them, does that mean your shaft plugs directly into J2?
No, this is JL. So this is the load, right? Right, that's the load.
That we're spinning with our motor.
Mm-hmm.
So, but
Through some gears.
But after we combine and figure out our gear N1 N2 ratio, is our motor connecting right into J2?
We're just doing the math for it, we're not actually removing the gears. It's just the math.
Yeah, so when we have a gear system, so let's say this is N1, that's N2. Okay? So let's call this theta 1. Let's say this is, we're going to call theta 2. What are the relationships that we derive between N1, theta 1, and N2, theta 2?
What is it that this means?
Do you recall? Is that it?
Yes.
Yeah? Okay, so yes.
So is that the reason why you have N1 over N2, because it rotates like clockwise? It was opposite direction, so you have N2 over N1?
No. This is just when you want it to reflect one side to the other side.
So you always go N1 over N2?
Now, depending on where you're reflecting to,
way, you say like this,
right? So,
this, you get this.
Alright. maybe let's do an example of this gear system to, so to write to find the equation of our gear system, we said the energy is the same. So T1, theta 1 is T2, theta 2. Do you recall? Right? So because there's no loss, right? The energy put in should be the energy that you're going to get out. And then, what is the other one? We said the distance traveled, S1, equal to the distance traveled by the other gear. So the distance traveled by S1 is at R1 what? The arc length is
R what, radius?
R1 theta 1 equal to R2 theta 2. Yeah?
That makes sense.
So, we have, and then what about the ratio? So if I have this, and I have this, what is the ratio? What is the gear ratio? Can you tell me? So this is, let's say this is R1, this is R2, and we have N1 here, and then we have N2 there. What is the gear ratio?
Into other one.
So if I do N2 over N1, what is that equal to?
The gear ratio.
Are you fit?
More teeth means a larger radius.
Yeah, right? So when we combine these two, so we have theta 1 over theta 2 is T2 over T1, isn't it? Are you fit? So theta 1 over theta 2, what is that equal to?
R2 over R1.
Right? So, can we pull all this 1, 2, 3 together?
Yeah.
That's the relationship between all three, right? And also, excuse me, do you agree that is this is angular velocity 1 equal to angular velocity 2? Do you agree?
You just,
Theta, d theta over dt is omega, right?
yeah.
So the ratio is the same.
Yes, sir. Yes, sir.
Yeah? So, when I have this R1, R2, and N1, and N2. Now, if I wanted to write the, so let's say this has a, so, and this is, let's say this is theta 1, that is theta 2. Okay? So let's do an example. So we had, what was that example? This example. So let me copy this example. So I think we definitely need to do a homework on this because I have a feeling that you guys don't read the notes. It's not good.
You mean the slide notes,
Yeah.
that, the ones that you don't cover in class? You said-
No, like this example.
Oh,
You don't
okay.
seem to remember.
I mean, I pay attention in class, but if you mean like outside of class, I go and read, look at the slides. Maybe. right now.
Okay. Alright, so let me copy this. Well, if you don't remember this, I don't know how you're gonna be able to do the homework.
Doing the homework will make it make sense.
So how come I?
Go to your office hours while there's no homework will make more sense.
Alright, so let me copy this. Okay. Now, so what we did, right, let's do this example again. What we did is to find the transfer function theta1 over t1. Okay? So, now, we know that if I know that, so what is the relationship between T1 and T2? What is T1 over T2? Side 1 and N2, you all confirm? So what is the relationship between theta 1 and theta 2? Read that, we just grab it. What is that? So R1 over R2? What is that in terms of N?
Or whenever R2 goes in, whenever
Okay. So, and then we say that this is T1 over T2. Are you with me? Okay. So, can we write the equation for the system? Can we write the equation of the system? Can we write theta 1 and theta 2? Can we write the equation here?
So is the load on the right or the left? So T2 is the, or
So,
theta 2 is the load.
Assuming this is the motor.
Okay.
The motor is on this side. And I'm using to drive the load. Okay?
And if it was inversed, then everything to the left would have N2 over N1, right? Squared.
Yeah, so what I'm saying is that if I wanted to draw this, as, so we have this, and then I have N1, I have N2, right? All the impedances that I have on this side, if I wanted to move them through the gear, what do?
Multiply them all by N2 over N1 squared.
The N2 over N1,
Uh,
moving this way,
oh, and then the other end.
okay? So N1 over N2 squared. So that multiplied by J, right? So let's say you have J here. J. And then you have and then we have this. You wanted to move it to the other side. What do we have? Have JS squared plus DS plus K theta 1 equal to T1. You all agree with that? Okay. So, and that's the equivalent, right? So we move everything, we remove everything, and we don't, so that means there's the equivalent to, I know that T1 is here, theta 1 is here. So the system that I have now is J times N1 over N2 square. I hope I put it correctly. So D N1 over N2 square K N1 over N2 square. We remove the gear ratio, right? We remove this. Yes.
So N1 over N2 depends on how big the gear is on each side, because it could be N2 over N1.
No, so what the direction we're moving to.
It's just how it's
So
defined.
we're reflecting everything here
So if you're reflecting everything on the
to,
other side.
to the N1 right to the N1 gear.
Okay.
So we reflected everything to the N1 gear, so we do N1 over N2, square multiplied by everything that I see connected to N2.
And there was a,
Reflecting to N2 is gonna be N2 over N1.
Yeah, right, so if you're reflecting that way, this way, then it's N2 over N1 multiplied by things that you see on the left side.
So basically, you just multiply everything on the right hand side by that, and you get rid of the gear ratio.
Yeah, so that's how to remove the gear ratio.
what would, it look like if we had an inertia from the motor side of the left?
Yeah, so you add it to it.
Okay, but that one wouldn't have the, cause you're basically, converting theta 2 to theta 1, right? And then,
Yeah.
but the theta 1 stuff is not gonna have that multiplier.
Yeah, right. Yeah, so, so when you look at, that's what I was saying here. So the motor has moment of inertia, okay? And it has some damping that associated with it. So when we reflect everything, what do we have? J on this side will be what? dA.
So is it equal to like a torque into the drive?
Plus N1 over N2 square times JL. Do you agree? We reflect this that way. Please talk to me.
Yeah.
We reflect this that way, right? And then the motor has D, like J associated with it, so we add both, right? We add them up. Are you clear?
Yes.
And then what about DM? So dA plus N1 over N2 square, yeah. Yeah?
Yeah.
So now we remove the gear ratio, right? We remove this. So we know what JM is, we know what DM is, we can plug that into our equation that we derived last lecture.
Yeah.
Right, so what are the equation we derived last lecture? Is it time to go?
Yeah, it's 112.
It's past.
Oh,
2 minutes.
But it's okay.
alright, so,
Really wish it was an hour and 15, actually.
what?
Really wish the time was an
Yeah,
hour
yeah.
and 15 minutes.
Absolutely. Okay, so now you know JM, you know DA, right? You know DM, you can just plug that into the equation we wrote initially. To get a transfer function. Okay?